All right. So continuing where we left. Yeah. Okay, sorry. So let's discuss what happens in this region here. Which means what if we start decreasing the VCE? Now, how do we? What were we doing previously? Previously, we were increasing this VCC. We were increasing from 2 volt to 3 volt, from 3 volt to 4 volt. So on increasing this VCC, we were increasing this VCE to higher values from 2 volt to 3 volt and so on. What we discussed is nothing happens. But what if we start decreasing this VCC and thereby then decreasing this VCE? So we know that this VCE, for example, if it is 2 volt, out of this 0.7 volt is dropped across this, and 1.3 is dropped across this, which is creating this sufficient reverse bias. This reverse biasing is important to attract the holes coming from the emitter, this P side. Okay. Now as we decrease this VCE, this will remain almost same, because this is governed by the, as you remember, the load line and the IV characteristics of a forward bias base emitter PN junction. So this one and this one, so operating point, so this remains same, which is VEB. But as we keep decreasing this, how do we decrease this? By decreasing the EMF of this battery VCC. The current remains same, because current is governed by this IB. Current is governed by VBE governs IB, and IB governs IC. So keeping IC constant and RC constant, so this IC/RC remains same as 1 volt. But let's say if this VCC starts to decrease, then the VCE, which is VCC minus IC/RC, will start to decrease. And for example, it will become 2 volt, from 2 volt to 1.5 volt, 1.5 volt to 1 volt, 1 volt to 0.9 volt, 0.8 volt, 0.7 volt. Now this VCE is equal to VEB plus VBC, and this is the reverse bias voltage. Now what if we decrease this? This remains same, so this reverse biasing decreases. So here I have there it is. Okay, I guess here, yeah. So in this particular example, if we decrease this VCE from 2, see, when VCE is 2, then 0.7 here and 1.3 here. When 2 will become this 1.5, then 0.7 here and 0.8 here. When this will become 1.2, then 0.7 here and 0.4 here. And when this will become, let's say 1 volt, then 0.7 here and 0.3 here. So 1 volt means 1 volt means, now let's say it becomes 0.9 volt, that means 0.7 here and 0.2 here, and then it will become, let's say, from 0.9 to 0.8, 0.7 here and 0.1. Now even this 0.1 volt reverse biasing is sufficient to attract the holes here. So as we keep on decreasing this VCE until this VCE becomes almost equal to, let's say, 0.8 or something, no problem. But what if we decrease this VCE beyond this, let's say 0.8, and let's say VCE is dropped to 0.7? So we know that this VCE is equal to VEB plus VBC, and this remains 0.7, and this is VBC. So this becomes 0, which means this becomes unbiased. Now as soon as it becomes unbiased, it has lost its property to attract the holes. So holes will be coming because of their own inertia kind of thing, because of the diffusion, and whatever holes are able to come in this side, that will be collected and sent here, thereby constituting the collector current. Some of the holes may be colliding and they may come to rest also. So not all holes may be able to come here. So therefore the collector current will start to decrease. Not only that, when we decrease this VCE, this voltage, to values even less than 0.7, so let's say this becomes 0.6 and this remains 0.7, so what will happen is that this will become negative. And what is the meaning of this becoming negative? For example, if this VC is 0.6, this 0.7, this becomes minus 0.1, and as we keep on decreasing this VCE and VEB, we are maintaining maintaining this constant voltage across the emitter base PN junction 0.7. Then this VBC becomes negative, and it becomes more and more negative. In fact, when VCE becomes 0, it becomes a very high forward biased. And we know that when this base collector PN junction becomes forward biased, instead of having an electric field like this was the electric field in case of reverse biasing. Now this electric field will become in opposite direction, because now it is forward biased. So P on the positive side and N on the negative side, and electric field is like this. So when this electric field is like this, it is repelling the holes which are coming from here, and so the holes which are coming from the collector, they will be repelled. So less and less number of holes will be able to come here and go here. As this forward biasing keeps increasing, when we decrease this VCE, this becomes higher and higher forward bias. Negative voltage here means forward bias, forward biasing. FB means forward biasing, RB means reverse biasing. So as we keep decreasing this VCE, forward biasing keeps increasing, and as the forward biasing keeps increasing, it repels more and more the electrons, it repels more and more the holes, because it is PNP, isn't it? It repels more and more the holes which are coming from emitter, and so the collector current will drastically decrease. So that is what we need to draw here, that as we decrease VCE, the VBC becomes forward biased beyond this 0.7 volt if we decrease it further. So on the forward biasing, so the higher is the decrease in VCE, the higher is the forward biasing. Higher forward biasing means higher repulsion to the incoming holes, and so the collector current will decrease, and the collector current will decrease on decreasing this VCE, and it goes something like this. So in this part, we say that the PNP transistor is in the saturation mode, and this is, we say that the PNP transistor in common emitter mode is in the active state or active mode. So active mode versus saturation mode. What is the saturation mode? When this base collector PN junction becomes forward biased. So in this saturation mode, what is controlling this IC? This VCE here. VCE is the controlling. So as we keep decreasing VCE, IC will decrease. So now we understood properly what are the two modes. So in one mode, IC is controlled by VCE, which is saturation mode, and in another mode, IC is independent of VCE and is controlled by IB, and this is called the active mode. Transistor as a switch utilizes the saturation mode properties, whereas transistor as an amplifier utilizes the active mode characteristics. Okay. So I hope this is clear. Now this is fine. Now this is at a particular value of VBE and a particular value of IB. Now what if we increase IB? What will happen? For example, in the active mode, when the collector base PN junction is sufficiently reverse biased. Now when this collector base junction is sufficiently reverse biased, then on increasing this input voltage, so increasing the input voltage means you know that the load line will be shifted like this, so current will increase, IB will increase, and we know that IC is equal to beta IB, so IC will increase, and when IC will increase, why IC is increasing is because of the increase in IB. IC is equal to beta IB. So in this active mode, if we increase IB, IC increases. So this is how the characteristic will look like for a higher IB. A higher IB will drive a higher IC. Now we discussed previously that the IC is equal to beta IB. But this is valid only when the transistor is in this active mode. Valid only in active mode. Why? Because in this saturation mode, we know that this collector base PN junction is forward biased, and it is going to repel the electrons, repel the holes which are coming from the, which one is this? Yeah. Or maybe I can draw a new diagram. It is going to repel the holes which are coming from here. So where is that diagram here? Okay, maybe this one only. So if this becomes more and more forward biased, it will repel more and more the holes coming from here. Now previously when it was reverse biased, irrespective of how much we were reverse biasing, it was attracting all the holes here which are coming from diffusing from emitter to collector. So what was controlling the emitter? What was controlling the collector current? What was controlling the collector current here? Holes coming here. Whatever were the electrons diffusing from emitter side were able to come to collector. So IC was controlled by IE or IB, whatever you call it, IB. IB is the input current. So IC was controlled by IB. Now, once this becomes once it becomes forward biased, so electric field will be like this, and so whatever holes are incoming, they will be repelled. So these holes, instead of going here, they are repelled here. So the holes have no other option to go like this, isn't it? And so the collector current is decreasing, or you can say that the base current will increase. So when it was in the reverse biased, this PN junction, and IC was equal to beta IB, not anymore in the saturation mode. In this saturation mode, this is not valid, because in the saturation mode, this decreases, this may increase, and so beta may change. So there is no particular beta, it all depends on how much forward biasing. The more and more you forward biases, the more is the decrease in the IC, and so we say that this equation fails. So remember that this is valid only for the active state, active mode. In the saturation mode, the current is controlled by VCE. IC is controlled by VCE and not by IB. So if we draw the IC versus